tell you is the way to find out the pi orbital symmetry using a Huckel's pi orbital method. Okay. So let's take a simple molecule NO2. NO2 is obviously pi orbital. This is what I'm going to do it. Let's take NO2. Its structure is you can say this is N plus O minus. This structure. So O minus plus. Okay. So it can be like this. So we take it will be nuclear. So I just take this one. We can take the this is C2V. This is C2V molecule pointed to C2V. So we can take the only pi orbitals. Okay. So you take the structure. Ground state. Let's take the ground state. All pi orbitals of NO2 and this PZ orbital. Just take PZ orbital. In that, the orbitals are coming towards us. Basically, this perpendicular to this frame up. So this is the skeletal sigma bond. So these bonds are coming towards us. We just assume like that. Considering that, we can write reducible representation. So I call this one as say phi 1, this is phi 2, and this is phi 3. Okay. This phi 1, phi 2, phi 3. And I'll also write phi 1 as equivalent to phi 3. And phi 2 is unique. So this is C2V. I think by this time you know what is C2V character table. So it was A1 is 1.11, A2 is 1, 1, minus 1, minus 1, B1 is 1, minus 1, 1, minus 1, and B2 is 1, minus 1, minus 1, 1. Okay. With this background, we are going to write the reducible representation for these pi orbitals. I just call reducible representation R. So we just take what we can see. We have to see all these pi orbitals. Pi 1, I mean, we have to just find out what happens when you perform these. So this will be with symmetry. Let's start with E. So all will be same. So it's not going to change. The reducible representation for E will be 3, and for C2. So say these orbitals are coming out of this board. C2 will perform. So the orbitals will go other side, and these two interchanging its position. So phi 1 and phi 3 will interchange. So that gets cancelled, and only this one gets. So unshifted atom is only this atom, a nitrogen atom. So only orbitals will be shifted from here to this one. Yes. So that is minus 1. Okay. Other two atoms are shifted, so that is considered as 0. Again, sigma V plane if you use, if you cut it through this, and then these two will interchange. Phi 2 will remain as such. So it is plus 1. Okay, this is plus 1. And last is sigma V double prime. So if you place the mirror on this molecule, so all the orbital will go back or inverted. So it's minus 3. So this is a reducible representation. From there, you find out what is the possible IRs, right? So we use the reduction formula and get reducible representation will be in the form of reduction formula. You have to use the reduction formula. And then find out if you do that. So what you will get? Can you try it? What you will get if you use the reduction formula with A1, A2, B1, B2? How many will survive? Will A1 survive with this reducible notation? I'll try one. Okay, A1 will be 1 over 4, 3 minus 1 plus 1 minus 3. So this gets cancelled to 0. So this A1 will not survive. A2 1 over 4. So 3 into 3 minus 1. Okay, so this is plus into minus. So minus 1, minus 1 is plus 3. So this will survive. 3 plus 3, 6. 6 minus 2, 4. 4 by 4, 1. So it will remain 1. Similarly, we can do it for other two, B1 and B2. So B1 will survive or not? I think I'm not doing anything new, so you're all aware of this. The reduction formula I'm using. So 3 to 1, and then minus 1 into minus 1 plus 1, plus 1 into plus 1, 1, minus into minus plus 3. So you get 3 plus 3, 6, 6 plus 2, 8, 8 by 4, it's 2. So the amount B2 will be 1 by 4, 3 to 1. So minus minus plus 1, minus into plus minus 1. Again, this will be minus 3. So this gets cancelled. So what survives this? We can say, we can say reduction formula. We use the what is surviving is 2 times of. Okay, so it's gamma of I just say A2 plus 2 times of B1. Okay, you get this when you reduce it. So you have you can say this pi orbital, whatever we call it. So you say pi orbitals. So A2 plus 2B1 you got. So next is now we are going to project it out, these orbitals. Okay. So next step is projection orbital we are going to use. Projection operator for A2 and B1. So now phi 3 and there are phi 2. You have two orbitals, unique orbitals, phi 1 and phi 2. So you have to project it out these two orbitals. Okay, let's start with what? Phi 1 orbital. So phi 1 you concentrate. Projection we are going to use. Okay, so project out. Can I write it there? Phi 1 and phi 3 with respect to A2 and B1. Because only A2 and B1 are surviving. So what I'm doing is I'm going to project out only these two orbitals, phi 1 and phi 3, with respect to A2 and B1, because only those two are surviving, whereas other two, A1 and B1 get B2 get cancelled out. Okay. So project out phi 1 and phi 3. So I'll just start with phi 1. Future. I'll do it here. Projection of phi 1 with respect to A2. So we wrote the formula now. What? 1 over h. Right here also 1 over h. So it's 4. So what I'm doing is it's a lengthy operator. Then we take the linear combination of orbitals. then we normalize it, and then apply Huckel's theory. Okay, so from that we get the energy levels. See, there are 3 orbitals, right? So in the end, you will find 3 energy levels for NO2 molecule. And after getting the energy levels, you also get the symmetry of the energy levels. Okay, so that's the target. So please keep watching. It's a long process. Let's try to finish it. So it's a 1/4. Project out means last class we said you have to multiply with the orbital character, and then with the symmetry operation, how it changes, right? So it is phi1. If you just concentrate on phi1, so what happens? If you perform E operation, it's not going to change. So it will remain as phi1 only plus C2. When you perform C2 for this molecule, yeah. So what happens? So it's rotated. These 2 atoms interchange. Phi1 and phi3 will interchange. So this is so atoms interchange phi1 and phi3. So wherever phi1 is there, phi3 will come with negative phi3. Okay, so because we are following phi1 only, after performing A2 operation, in A2 we are multiplying with 1, and then C2 we are performing, it is phi3 will come there. Okay, and next is sigma V. If you perform sigma V, phi1 will become again phi3. If you place a mirror across this, phi3 will go to the phi1 place. That's why I written phi3. And this is A2, right? A2 is -1. So I'm just again minus and putting that. But here the sign is not changing. Okay, so the plus will remain as plus, but only the orbital will shift its position. And last one, sigma V. If you slice it, this molecule into 2 half, into all 3 atoms, slice it. Orbitals will be split. So phi1 will remain as phi1. Okay, phi1 will remain as phi1. But the orbital will go other side, so minus will come. But here it is A2, minus is there, so you have to multiply with another minus, so it becomes plus. Okay, so I close this. All 4 is done. So if you do this, so you get what? You get 2/4, so 2 times of this. So it's 1/2, phi1 minus phi2. Okay, so this is projection of phi1 orbital with respect to A2. Projection of phi1 orbital with respect to A2. Now let's do projection of phi2 orbital with respect to A2. Yeah, so this is 1/4 again, 1/h. Now phi2. Now we are going to follow the phi2 orbital, project out with respect to A2. Okay, so phi2, if you perform E, it's not going to change. Phi2 will remain as phi2 plus C2 to perform, it becomes negative. Negative phi2 goes to other side, the phi2 orbital, and A2 is positive, so it's again negative remains. Third is sigma V. So apply sigma V on this orbital, phi2 orbital. It's not going to change. Phi2 will remain as phi2 plus only. So plus will be there, but there is a negative here, so I'm going to put plus into minus here. Okay, so that's minus phi2, and then last one is sigma V double prime. So slice it. Phi2 will go to phi2 only, but negative phi2. Again, here is negative sign is there, so this becomes plus. So what happens here? So you have 2 gets cancelled, and these 2 gets cancelled. So this is project out, it just annihilates. Equal to 0. Okay, projection of phi2 orbital with respect to A2 is 0. Okay, I hope you're following it. Those who are awake, huh? If you don't follow it, just ask me, and I can redo it. Let me finish other 2 also. Okay, now we have done A2. Let's work out for B1. Fine. Okay, so let's do B1. Huh? Projection of phi1 orbital with respect to B1. Yeah, so projection of phi1 orbital with B1. Yeah, again, you have to follow with this one. So let's see, B1 is not going to change, 1 over 4, phi 1 orbital, right? So B1. So phi 1 is, if you perform E, not going to change, phi 1 is minus phi 1. If you perform C2, it becomes phi 3. Okay, so it becomes phi 3, and then you subtract, to multiply with minus 1. Phi 3 it has come, minus phi 3, again it becomes plus phi 3, because you're multiplying with minus 1. Then again it is going to be phi 3 by sigma v plate, to place a mirror across, and then phi 1 will become phi 3. Then the plus will be, this will be just plus, but B1 is plus, so it is plus phi 3. It is going to be plus phi 3. Place the mirror, and then orbital will just overlap on phi 1, so it's phi 1 become phi 3. So plus, and also here plus. Last one is going to be phi 1. If the perform is not going to change, but we can go to the other side, minus will become, but here B1 is minus, so minus minus plus. Okay, I am getting like this. So 2 times of phi 1 plus 2 times of phi 3. So this is 1 over 2 phi 1 plus phi 3. So if you project out phi 1 orbital with respect to B1, we get phi 1 plus phi 3. Okay, the last orbital will come. Projection of phi 2 orbital with respect to B1 symmetry. Okay, so that's last one, phi 2 orbital with B1 symmetry. So again, it's 1 over 4. It's something similar here. Phi 2 is not changing, so we just write. So E, if you perform phi 2 will remain as phi 2. Then if you perform B1, phi 2, C2, so it's minus phi 2. But B1 is minus 1, so it becomes plus. Again, this will remain phi 2. Perform sigma V. So it's not going to change. I'll keep it as this. So it's plus phi 2. Last one is phi 2 orbital with sigma V planes, minus phi 2. Minus phi 2 minus phi 2. This is minus phi 2. But you got multiply with minus 1. So it is plus 1, plus phi 2. So that's I'm projecting out. So it becomes 4 times of phi 2. So answer is just phi 2. Okay, so this is the projection of phi 2 with respect to B1. Now we have 4 results, right? So first one is this, and then this is 0. Third is this one. And last is this. So what we have done is we have taken orbitals. To summarize, phi 1 and phi 3 are unique. Phi 1 and phi 3 are similar. So we are taking equivalent, and then phi 2 is different. So phi 1 and phi 2 is different. We're projecting now these two orbitals with the symmetry, which are when you reduce it, which are surviving. So with that symmetry, we are projecting out. So we got 4 equations. You can say phi 1 orbital A2, phi 2 orbital A2, which is 0, and then phi 1 B1. Okay, so now I erase this side. Now I don't need this shape. So I call these one as various orbitals, phi 1, caps phi, or just small phi. When you take the linear combinations, you get. So I just number it. It's just 1, 2, 3, and 4. Okay. I'm just numbering out these things. Now I'm going to take the linear combinations. Say 1 plus 2, and then 1 minus 2, 2 plus 3 plus 4, 3 minus 4. So we're going to take the linear combinations. So I call it as 1 plus 2. Okay, so the symmetry will be conserved, you can see. So this is 1 over 2, phi 1 minus phi 2, phi 3. Okay, and then 1 minus, say, you're going to take 1 minus 2 also to perform. It's same, okay? So 1 plus 2 are equivalent to 1 minus 2. If you do that, it's going to be same. So we just take only 1. So 1 minus 2, we don't do it. So other linear combination is 3 plus 4. So 3 plus 4. So 1 plus 2 symmetry is A2. This is important. Huh? So this symmetry is A2. Whereas 3 plus 4, if you add it, so we get 1 over 2 phi 1 plus phi 3 plus phi 2. So you get something like this, right? So you can and again we have to subtract the 3 minus 4. So this symmetry is B1. 3 minus 4 again it will be different. So it's 1 over 2 phi 1 minus phi 2 we get. Okay. So this can be written in terms of, again, the symmetry is B1. Huh? So both are B1. So this can be written how? I mean, for we are going to take the integral. So what I do is I slightly change it in different form. I'm going to write this as, I didn't put a bracket here. Phi 1 plus phi 3 plus 1 over 2 phi 1. So this is B1 symmetry. So again, I'm going to do this change, small change. So 1 over 2 phi 1 minus we got phi 3 plus 1 over 2 phi 1. So this is again B1 symmetry. Okay, so let me check with my notes. So this is fine. 1 over 2 phi 1 minus phi 3 plus 1 over 2 phi 3. Is it phi 3? No, it's not phi 3. It's phi 2. Okay, hope you guys are awake. I'm adding C wrongly. It's phi 3. Okay, I just simply expanded the equation. That's it, nothing else. I just added 1 and 2. Subtracted also going to be same. So this is A2 symmetry, and then 3 plus 4 and 3 minus 4. I just wrote. Maybe I just subtract, remove the brackets. So now I call these orbitals as phi 1, the capital phi. Okay, so this is phi 2, and this is phi 2. Okay, so I'm going to call these orbitals. Phi 1 as 1 over 2, phi 1 minus phi 3, and then this is phi 2 as this one, and phi 3 as 1 over 2, phi 1 minus phi 2 plus 1 over 2, phi 3. Okay, so with this projection part is over. Generally, when you take orbitals, no, we generally normalize it. Otherwise, it will have no meaning. With respect to 1, we normalize it. When you normalize it, normalize phi's. So all these phi's are normalized. So phi 1 will be, I would say, it becomes root 2 by 2, phi 1 minus phi 3. So this is A2 symmetry. Phi 2 will be. I give the answer. You work it out how to normalize it. Okay. As a homework, I give you. So orbitals are going to be same. Only the nominal constant will be different. So it is 1 over 2 phi 1 plus phi 2 plus phi 3 of phi 3. This is B1 symmetry. Similarly, for phi 3, it will be square root of 2 over 3 1 over 2 phi 1 minus phi 2 plus 1 over 2 phi 2. So again, this is B1 symmetry. So you have 3 phi's. After normalization, you get something like this. Okay, normalization, how do you do? Any function, n square, say psi square equal to 1, right? So that's what, I mean, we have to just multiply with n and then equate to 1 and find what is n, and then substitute back in the same equation. So that you get the normalization constant. So these functions have been now normalized. The equation has been normalized. So when you normalize it, you get root 2 over 2 instead of 1 over 2. And this part, whole thing remains, but here there will be a normal constant root 2 over 3. Again, phi 3 is root 2 over 3. Okay, so we get 3 equations after normalization. Now I'm going to apply Huckel's pi orbital method. I'm going to use a notation which some of you may be familiar. So say Huckel's, what they did is Huckel's method. So they considered, it's mostly for pi orbitals, right? So instead of considering the total Hamiltonian, Huckel's method takes the effective Hamiltonian. Effective Hamiltonian means you separate out the sigma bond electrons and pi electrons, and then call that as a effective Hamiltonian. Okay, so since we are interested mostly on pi orbitals, we are interested on only the energy change of pi orbitals. So the total Hamiltonian is given as sum of, you can say sum of 2 Hamiltonians, one for sigma, one for pi. So H effective is so this is this becomes separated. Sigma electrons put it in sigma. I mean electrons involved in the sigma bonds are considered separately, and pi electrons are considered separately, and we call it as effective Hamiltonian. When you do that, so basically then effective Hamiltonian is after all the derivations. I think we'll see this how we are getting it. It ends up with after a lot of derivation, we end up with H effective as the H4 plus 2k minus L. 2k minus what? Or 2j minus k. So you end up something like this. These are all operators. I would say J operator, K operator. Yeah. So J is the what? J is the Coulomb operator. K is the exchange operator. So this lowers the energy. So all the sigma electrons are taken into in core. So you just separate it out, and then you write H effective as say if it is neighboring atoms. If there are pi orbitals, if there are 2 neighboring orbitals are involved, say RR, then you call it as alpha. So effective pi orbitals, only pi orbitals are considered, it's alpha. So if it is H, RS, effective pi orbitals, we are considering only pi orbitals. Then if they are RS, it could be beta or 0. When it is beta, when RS are nearest neighbors or just neighbors. Okay, if RS not neighbors. So this is the roughly you can consider this. So basically in benzene or I would say, yeah. So in any example you take, three system system you can take. So benzene you can take, right? So you have 6 pi orbitals. So you separate the problem into sigma into pi. So sigma frame up is just taken separately, and you have pi orbitals. And if these two orbitals are considered nearest, so they are called as alpha. And if okay, if both the atoms are same type, then it's alpha. If it is in this case all carbons are same, so it could be only RR, or if you consider the product of this into this, it's not a nearest neighbor, this carbon, so this becomes 0. Okay. If you take like in our example NO2 we are taking, NO2, so we have pi orbitals, 3 pi orbitals. So if you take these two orbitals, they are nearest neighbors, they are R and S. So this is considered as beta. And if you consider this and this orbital, they are not nearest neighbors, so that is 0. And so like this you will get it. Alpha, beta, like that. Okay. So if it is, we are considering phi 1, phi 2, phi 3, no? So like that we just take nearest neighbors. If both are same, then it is alpha. If it is neighbors but they are different, is beta. If they are not neighbors, it becomes 0. So with this background, we are going to use this theory to get the orbital symmetry. So HFQ, let it be like this. For reference. So now we have phi 1, phi 2, phi 3. So we are going to use this Hamiltonian. The H we have HFQ. Phi, you can say, and then you take a phi 1 and phi 1. Okay, if you integrate it, you get energy, right? So variation principle, I think you know. So variation principle, the energy you can get by what? So this is psi bracket notation. You're aware? No, I just use this representation. B tau. Consider psi is optimized, so you can get the energy by taking this equation, by solving this equation, right? Psi h psi integral, then you get the energy. So that's what we are doing here in Hussels phi orbitals. So you take the phi 1 of A2 symmetry, you apply the Hamiltonian, which is effective Hamiltonian, and then phi 1. So if you do this, you will end up with what? So root 2 by 2. Twice you get square. I just take out this constant, and then phi 1 minus phi 3 h, and then phi 1 minus phi 3 you get. So this is h effective. You can say eta. Okay, so it's integrated. So if you solve this, so phi 1 h, phi 1 is basically it is alpha 1 with some constant. So it's a 2 by 4, it's 1 by 2, right? It's 1 over 2 is a constant. So it's phi 1 h, phi 1 is alpha 1. So phi 1 h, phi 3 is minus 0. And phi 1 h, phi 1 is 0. Phi 3 h, phi 3 is minus plus, so phi 3. Phi 3 same, so it's alpha, right? If you solve this, it's alpha 3. Is correct? So alpha 1, alpha 2 doesn't matter, so we just remove this subscript. So alpha, it's just alpha. Phi 1, it's just alpha. And then phi 3 is alpha. So it is 2 alpha by 2, so it's end up with alpha. The first equation is alpha. Let's do the second and third and finish it. So we're getting the alpha is the energy, okay? So alpha means it's a alpha is a Coulomb integral. You can say Coulomb energy or Coulomb integral, and increases the energy. When you have this integral, then the increase energy. Beta is exchange integral. Exchange integral decreases the energy of the molecule. Okay, so this is the logic. Alpha increases the energy and beta decreases the energy. So with this in mind, we have taken phi 1. Now let's go to the phi 2. Okay, the integral of phi 2 h effective for pi orbitals, and then phi 2 d tau and d tau. So if you do this, we end up with 2 by 3. So we can write the equation. So it's 1 over 2 phi 1 plus phi 2 plus 1 over 2 phi 3 h effective phi orbital, and then again with that again the same thing. So it's 1 over 2 phi 1 plus phi 2 plus 1 over 2 phi 3. So you get something like this, and then you solve this. This phi 1 into phi 1 with h, it's alpha. So 1 over 4, so it's 2 by 3. 1 over 4 alpha. Phi 1 h, phi 1 is alpha, plus phi 1 into phi 2, it's beta, but 1 over 2 beta. No, it's not 1 over, just beta, and then, no, 1 over 2 beta. Okay. So the phi 1 into phi 3. So it's 0, plus 0. Plus, now you have to take phi 2 orbital, phi 2 into this one. So again, it is 1 over 2 beta. Then this with this, so plus alpha, you get this with this, phi 2 and phi 3. It's 1 over 2, 1 over 2 beta. Now you take phi 3, so first term is 0 because phi 3 and phi 1, it's not nearest neighbors. So phi 3 and phi 2 are nearest neighbors, so it is 1 over 2 beta plus 1 over 2 into 1 over 2, 1 over 4 alpha. So you get so many terms, so 0 gets cancelled. 2 terms get cancelled because they got 0. They're not nearest neighbors. So if you solve this, you get what? The 2 by 3, 1 over 4 alpha plus 1 over 2 beta, 1 over 2 beta alpha plus beta 1 over 2 this. So if you do this, you'll end up with energy of alpha plus 4 by 3 beta. So just simplify it, you'll end up with this one, alpha plus 4 by 3 beta. So this is for the phi 2 orbital of B1 symmetry. So this is A1 symmetry, this is B2 symmetry. Okay, we are taking symmetry is conserved. So it's A2 and this is B1. Yeah, similarly do it for the third orbital. So phi 2 H effective phi 2 d tau. So phi 3 you are take phi 3 the third orbital. So similarly you have to do this. The sign will be different. If you expand this, you will end up with alpha minus 4 by 3 beta. Okay, of B1 symmetry. So you get something like this. So now we have 3 integrals. One with alpha energy of alpha, other with energy of alpha plus 4 by 3 beta, and third is alpha minus 4 by 3 beta. Okay, so now this can be energy orbital can be drawn. I mean the orbitals can be drawn with the energy ordering also you can find out. So alpha we got. So this is alpha plus 4 by 3 beta. Okay, so in O2, as I said, I started with the 3 orbitals will be 3 energy levels will be there. Well, we consider 3 orbitals. When you have that, alpha is the reference. Okay, this is alpha, and this will be alpha plus 4 by 3 beta, and so energy access to plot. And third one is alpha minus 4 by 3 beta. So you have three energy. Alpha is a reference, and that beta is an exchange integral. So it lowers the exchange, or you can also call as a resonance integral beta. So it lowers the energy beta. That's why it is brought down. Is this correct? No, it should. So beta is negative. As such, beta is negative. So this is going to be plus beta, and this is minus. Beta will be negative. Okay, so negative of negative should become positive, so it just erases it. So you have three. So in NO2 molecule, we consider this one, right? O minus plus. So if you draw that the structure, it will be bonding orbital here. I mean, completely, and this will be alpha plus beta is what symmetry? This is B1 symmetry. So this is B1 symmetry. Alpha plus 4 by 3, and second one alpha will be of this form. It will be a kind of a lone pair. It just exists like this. Again, this will be alpha I got from first equation. So there is A2 symmetry. And then a third one, alpha minus 4 by 3 beta. Okay, so again, this will be B1 symmetry. But orbital, if you plot, it will be something like this. The electron density, if you plot the electron density, it will be separated. So it will be something like this. So we got, and this is the solution. So basically, we started with pi orbital symmetry of NO2 molecule using Huckel's method. So the symmetries are three orbitals. NO2 molecule, we have three orbitals. Its energies are alpha plus 4 by 3 beta, alpha, and alpha minus 4 by 3 beta. And symmetries are B1 has the lowest one, B2, and then A2 is the second orbital and shape. Third one is B1 symmetry. So like this, one can find out for any given molecule. Benzene, if you take C6H6, right? So it will have 6 energy levels. Okay, so one can find out what is the resonance energy also. And then stabilization energy one can find out from this. So this is a long process. So what we have done is we started with NO2 C2E point group, and then we wrote we consider three orbitals, phi 1, phi 2, phi 3. In that we wrote the reduction using basis we wrote considering the orbitals. So we got the basis, reducible basis. From that, we use the reduction formula to get the irreducible basis. So A1 and B2 times of B1 were surviving. So with that in mind, we started going ahead, used projection operator, which we learned in last class. So projection operator, which orbital survive, which orbital doesn't survive. We just saw that. With projection operator, we got three functions. One is 1 over 2 phi 1 minus phi 3. The other is 1 over 2 phi 1 plus phi 3 and phi 2. Then we took the linear combinations of all these three equations. So we got three set of equations. And then we normalized it, but I didn't give the normalization how we do it. So you please work it out how to normalize the orbitals. Okay, you normalize it. After normalization, we use Huckel's theory. So obviously, two atoms are neighbors and they are equivalent. We call it as alpha. Label we give. If the two orbitals are not same, it is beta. And if the two orbitals are one and distant neighbor, then it is 0. So considering that as our notation, we expanded, we solved this integral phi 1 h effective phi 1, and then phi 2 h effective phi 2, phi 3 h effective phi 3, and then got the energy levels of particular symmetry. So A2 has one energy level, alpha has A2 symmetry. Other two energy levels are having the value of alpha plus 4 by 3 beta and alpha minus 4 by 3 beta with B1 symmetry. And And if you see the equation, so wave function you can write, right? So if you get the wave function, if you plot it, you will be in this form. So one can do same thing for benzene or any pi system. One can write it. Okay, it's a long process, so I just stop it here. If yeah, okay, maybe next class we'll try for some other molecule so that you can appreciate it better. And after this, we go for the metal carbonyl metal complexes. There also we use this precisionometer. The method is same, but yes, there it involves d orbitals also. Okay, so a lot of people uh, uh, left, it seems. So it's half of the class remaining. Um, Fine. So this is a long process, but yes, once you do understand what we're doing, then it should be applied for all other molecules. Then you will appreciate it better. Okay, I'll stop this recording.